As we've been working through the details in week 4, we've looked a lot at parallels between sums and counts and between proportions and averages. But because this can be pretty dense material, we're taking it in fairly small chunks. So after having worked with sums and averages, we're now going to do some parallel explanations for sampling distributions of counts and proportions. So first thing, now we know that counts can be represented as sums, which means the central limit theorem we used for sums also applies to counts, except counts are always a little more complicated, and in particular the central limit theorem for binomial counts depends on both the sample size n and the population proportion p, and not just on the sample size n. Now, this area has been re-investigated in the last 25 years with computers. You might think we have it all figured out, but with computers to help us do simulation, several researchers have taken a new look at this. Baldi and Moore have the references for this. It turns out that some combinations of n and p are just particularly snarky. So we're going to have some advice from Baldi and Moore, where we're going to say binomial counts are approximately normal when both the expected number of yes, which we know is n times p, and the expected number of no, which would be n times 1 minus p, when both of these are greater than 10. So this is in the reader in section 9 with quite a bit of illustration. It's summarized for you in Baldi and Moore on page 299. So let's go back and look at spike plots for binomial counts, kind of our starting point. This is what is going to happen if we have n of 100 and a population proportion of 0.12 or 12%. Now, we made a point of saying earlier that this sampling distribution was going to be really perfectly symmetric only if the p is a half. But you know, this looks pretty good. This looks like a symmetric mound-shaped, bell-shaped distribution. And if you work out the expected number of yes and the expected number of no, that's simply 100 times 0.12 or 12, and 100 times 0.88 or 88. And so both of these expected counts are greater than 10. And so the normal approximation for binomial counts may be used here. You don't have to use it, but in this situation, because of the way that picture looks like a symmetric normal curve, the normal approximation will be fine, and the conditions Baldi and Moore are suggesting to us will be satisfied. So I'm going to walk you through a series of graphs that are meant to illustrate that the combination of n and p matter to get the normal shape for distributions for counts and by extension proportions. And what I want to tell you is that when we're working in public health, small population proportions are quite common. If we're looking at rare diseases or rare mutations or other characteristics, we need to be able to work with small population proportions. And all these slides are in the reader, but again, I'm hoping that doing this in a spoken form may make the material a little more accessible. So this is just an illustration. Here's what we have for the binomial distribution of counts for a sample of size 80 and a population proportion of 0.02 or 2%. And we get something that looks like this, which I hope you will agree is highly skewed. If we apply the checks that Baldi and Moore gave us and work out the expected number of yes, n times p, and the expected number of no, n times 1 minus p, what we get from 80 times 0.02 is 1.6 for the expected number of yes. And it doesn't matter that the expected number of no is 78.4, once you see that the expected number of yes is 1.6, the kindest thing I can say is that the normal approximation is not wise. So let's keep going. Suppose we increase the sample size and we look at an n of 160, again with the p of 0.02. Well, this time the plot looks a little better, but quite frankly, there's still some skewness, and I haven't plotted the whole thing to give us a better graphic. For a proportion of 0.02, by the time we get to about 10 yes, the probabilities get really tiny. So I only plotted for the number of yes less than 40. Well, what happens if we work out our expected numbers of yes and no? 160 times 0.02 is still 3.2. 160 times 0.98 is 156.8. Your expected number of yes and your expected number of no should always add up to the integer that's your sample size. So here we are again. The expected number of yes is 3.2. Normal approximation, still not wise. Okay? Even though the sample size of 160 sounds pretty decent. So at the end of the day, we're going to take it up to an n of 640, which sounds like a pretty large sample size indeed. Again, p of 0.02. And again, I haven't plotted the whole distribution. I've just plotted for the number of yes less than 40. You know what? This is pretty nice for the normal curve. And if we figure out our expected number of yes and expected number of no, now we get 12.8 for the expected number of yes, 627.2 for the expected number of no. But here at last is an example that satisfies the criteria Baldi and Moore suggested for asking if we could use the normal approximation. And again, I've said here, the normal approximation may be used. 21st century, you don't have to, but in case you read literature that uses it, I want to give you the tools to check whether that use was wise or not. So, sampling distributions for p hat, quite frankly, are more useful than counts. Again, because they allow us to compare results from samples of different sizes. And again, this is a framework we're repeating over and over. The sample proportion p hat estimates the population proportion p. We're thinking about lots and lots of samples, which gives us this theoretical creature, the sampling distribution of p hat. And I know this is a little tricky because in most applications you have exactly one sample. And thinking about the behavior of sample proportions from many, many samples seems a little abstract, but it's the way the theory gets built up, and so I hope with repetition it gets a little easier to work with. So the other thing is, in our work here, Baldi and Moore, chapter 13, we're still looking at the behavior of p hat where we know everything, in particular where we know the population proportion p. And again, we're going to ask for a particular situation 3 questions. Given p and a sample size n, 3 questions about the sampling distribution of p hat. We've already worked out the mean and variance. The question that's left for us is the shape of the sampling distribution. So here's the facts, so we have them handy. We worked out for the sample proportion of p hat, the number of yes over n, that it was a linear transformation of a count. So we worked out that the expected value was the population proportion p, and we worked out the variance was p times 1 minus p over n, and of course the standard deviation of p hat is just going to be the square root of that. And so finally, here's the cartoon illustration scanned in from figure 13.5 for Baldi and Moore. And basically, they're a little optimistic because they don't tell us the sample size. They know very well that this distribution is not going to look approximately normal unless the number of expected yes and the number of expected no are large enough. But the bottom line for us is that the shape for a p-hat distribution is going to be approximately normal curve when the distance of the count is. So you have everything you need to check when we can look at a sampling distribution of p-hat and work out when we have license to use the normal curve if we want to.